All right, hello everyone, and welcome back to GRASP's Student, Faculty, and Industry Talk Series. This week, I'm very excited to introduce our first internal speaker of the semester, Tahiya Salam. She's a third-year PhD student in ESE, and she works in the Scalar Lab with Professor Ani Shea. Before her time at GRASP, she was a student at the University of Virginia, where she obtained dual degrees in math and computer science. Since she came to Penn, she's gotten her Robo Masters and has done some fantastic research on multi-robot teams and their interactions with dynamic environments. She's received many rewards over the past years for her work, including an NSF Graduate Research Fellowship and the Dennis R. Washington Leadership Graduate Scholarship. Outside of the lab, she's also been an invaluable leader in educational outreach here at GRASP, where she's been the program director for our AI for All summer camp, which gives opportunities for high school students from underrepresented groups to learn the fundamentals of AI and robotics. We'll be learning a little bit more about that program at a later SFI talk this semester, but today she's going to tell us about her recent research, which she entitled Learning Environmental Models with Multi-Robot Teams Using a Dynamical Systems Approach. So without further ado, I'll turn it over to Tahiya so we can get started.
Thank you for that introduction, and thank you everyone for coming to my talk. So we'll just jump right into it. Robots are a really great tool for environmental modeling and building maps. And in this talk, we're going to use these two terms, modeling and mapping, interchangeably. And so why are robots so good for this? Well, first off, they have onboard sensors, they have mobility so they can move around and sample the environment. They have computational capabilities for storing algorithms and maps. And most importantly, all of this can be done in real time. So robots are really powerful when it comes to sensing and tracking natural phenomena. But as you see here, these processes could be really different. It could include things like wind conditions in the atmosphere, surfaces of other planets, or physical and chemical phenomena underwater. So being able to understand and characterize these environments deepens our understanding of the world. And this is really important in general, but especially important for climate change and understanding the processes surrounding climate change. However, as important as these processes are, they're not easy to understand. A lot of times they're inherently complex. And so in order to operate in these complex environments, robots should be able to model these phenomena. And in turn, this will allow robots to perform in more realistic scenarios. So there is this interplay between modeling and accurate modeling and functionality of robots themselves. And so mapping complex environments is really pivotal and paramount to the success of these multi-robot teams. But as we mentioned before, these environments can be really different, such as fluid flows, space, or the ocean. And so even though these processes, these environmental processes that we're trying to describe in all of these robotic applications are really different, they can all really be unified under a dynamical systems lens. So in dynamical systems theory, what you're saying is that you have a state, and that state varies in time, and now you have a framework for studying the evolution of that state. So if your environment is changing in time, like wind conditions or the surface of the planet you're exploring or the species in the ocean that you're tracking, it can really all be analyzed under this dynamical systems framework. And so the methods that we're going to focus on in this talk lie at the intersection of these three fields: dynamical systems theory, machine learning, and robotics. So from dynamical systems theory, we're able to understand the process and its key features. So we have interpretability and domain knowledge from years of mathematical and physics research that elucidates what exactly is important about these processes. From machine learning, we have these data-driven methods that allow us to actually represent these dynamical systems. And from this, we also have tools to quantify uncertainty and some tools for dealing with incomplete data that we'll talk about later on. And then from robots, we have this inherent capability of how to do distributed computations, which is so necessary when you're working with multi-robot teams. And we also have this long-standing body of work that's related to how we build and modify maps of the environment from noisy data. So really the question that we're trying to answer is how can we build models of dynamical systems using machine learning, and most importantly, how can we employ these techniques on board robots? And so we're really interested at these techniques that lie at this intersection. And so the description of the environment as trying to represent a dynamical system allows us to use all of dynamical systems theory in trying to identify what exactly are the dominant spatial and temporal characteristics of the system. And the hope here is that we'll be able to use those dominant spatial and temporal characteristics in planning and control. And so two big challenges to representing dynamical systems is usually they're non-linear, and also the equations describing the system are often unknown. So when the equation is linear, when we have x dot equals ax, we have bountiful tools that allow us to analyze the system, and it's much easier to work with than these complex nonlinear systems. And when the equations are unknown, we don't have the same prior knowledge and tools for describing the evolution of the system. And so these are two of the key challenges that we address in our work. And so some of the machine learning approaches that that are popular in studying dynamical systems are deep learning, representations through transfer operators, and dimensionality reduction. And so we talk about these techniques that are at the intersection of dynamical systems and machine learning because they really focus on this problem of how do we make these data-driven models for representing dynamical systems. And of course, in robotics, we have data that's collected from the robots. And so I'm throwing this out there now. Deep learning is a really popular approach for representing dynamical systems from data. Unfortunately, we're not going to cover this, so I'm sorry if you were expecting this to be a deep learning talk. Instead, we're going to focus mainly on these dimensionality reduction and transfer operator works that really serve as the foundation for the ongoing work that we've been doing. So something that my lab mates and other people that know about my research know is that I'm really excited about transfer operators. And so we're going to introduce this notion of transfer operators. And just to motivate it, I want you all to walk through a little thought experiment. So say you have a cup of coffee and you stir in a little teaspoon of milk. The first question I'm going to ask you to think about is, can you predict where individual milk particles will be after 1 minute? And so it's not a trick question. The answer is no. The motion of the milk particles is chaotic, and it's really hard to determine the individual trajectories of milk particles. So the second question I'm going to ask is, can you predict the density profile of this milk after 1 minute? And the answer is yes, it'll be nearly uniform. After 1 minute, the milk will have likely uniformly spread in this cup of coffee. And so the insight here, which is really important in transfer theory, is that sometimes it's easier to predict the behavior of large collections of initial conditions, so what happens overall to this teaspoon of milk, than to predict the behavior of individual initial conditions. So where do these individual milk particles go? And this insight is actually leveraged in the theory of transfer operators, where the goal is to study the action of a dynamical system on mass densities of initial conditions. So not individual initial conditions, but mass densities of initial conditions. Unfortunately, we're going to have to get into a little bit of math. So in order to introduce the notion of transfer operators, we first need to introduce a transition density function. So we have some stochastic process denoted by x, and we have this time lag tau. And so this transition density function, this lowercase p sub tau of y given x, describes the conditional probability that at time t plus tau, the process takes on a value y, given that at time t, the process took on a value x. So just to reiterate, it's saying what's the likelihood that the process at time t plus tau is y, given that at time t it was equal to x. And so the two main candidates for analyzing a system using these transfer operator based approaches are called the Perron-Frobenius and Koopman operator. And so what's really interesting, one of the things that are interesting about these two operators are that they're both linear and infinite dimensional. So your system could be nonlinear and the state space could be finite dimensional, but when you are applying these transfer operators, they're lifted to a linear infinite dimensional space. And so the Perron-Frobenius is acting on these probability densities F, and it's referred to as a push forward operator on densities F, while the Koopman operator is a push forward on observables G. And so these transfer operators play a really important role in analyzing complex dynamical systems globally. So the fact that they are looking at these mass densities really gives us a global picture of these dynamical systems. So for example, you can use the eigenfunctions of these operators to detect metastable sets, which we'll get into a little bit later. You can use them to project the dynamics onto the dominant slow processes, or you can use them to separate signals that have been superimposed. Another really important thing to note about these operators is that they are adjoint to one another. And so it shouldn't really matter which one you use because you can derive the other from knowing just one of them. Even though this is true, there have been different methods and areas that have used one operator versus the other. And part of this has to do with the fact that the Koopman operator actually describes the evolution of observables. And observables could be things like measurements or a sensor probe. And so there's a connection to robotics where this evolution of observables could be representing the evolution of onboard sensor measurements that we're collecting with our robots. And so there have also been some dimensionality reduction techniques used to study this Koopman operator, which we will describe next. So why use dimensionality reduction techniques? Data from the real world, especially when it comes to things like fluid flows, can be really high dimensional. And performing calculations on and interpreting behavior about, and also just dealing with high dimensional data is really difficult. And so in machine learning, we have these dimensionality reduction techniques that says we have high dimensional data and we want to convert it into a meaningful representation that has lower dimension but still has key characteristics. So in this setting, we have a snapshot of data, X, that describes the state at time T, and N is a really large number. So principal component analysis, or PCA, also called proper orthogonal decomposition, POD, KLE, which I'm not going to try to pronounce what those letters stand for. It goes by many names in many different fields. And so this is a method for feature extraction from a data set that says, how can we reduce the dimensionality of the representation of the data while still maintaining as much statistical information possible with respect to variance? And so this involves creating a covariance matrix K, where this covariance matrix describes the spatial correlations of the data. And PCA represents the data set as a set of new orthogonal variables called principal components, captured in these phi sub i's. And these phi sub i's try to represent the patterns between observations in the data set and can represent the key spatial characteristics of time series data. So another framework in this dimensionality reduction field is called dynamic mode decomposition. And so in dynamic mode decomposition, the thing to note is that we assume snapshots are related via a linear mapping. So we have snapshots X that go from time 0 to t-1, and snapshots in the matrix Y that go from time Y to t. So it's just, Y is just a time-shifted version of X, and they're related by A. And so in DMD, you have this time series data, and you use an approximation of A, which you can decompose to get a set of modes, and each mode is associated with a fixed oscillation frequency captured in phi and a decay or growth rate captured in lambda. So you have this inherent notion of time and growth rates and frequencies. So you have this temporal component in DMD, which is inherently lacking in PCA. So DMD is actually an approximation for Koopman operator. There are tons of papers that show the connections between the two. And so this connection is actually what allows for this physical interpretation of the modes of the system. So this talk, we're really going to focus on how multi-robot teams can learn models of dynamical systems that represent the environment. And we're going to leverage techniques from machine learning to represent environmental models and use these models for planning. So we're really trying to blend strategies from the robotics community that focus on coordination strategies for distributed teams, and strategies from the machine learning and dynamical systems that focus on sophisticated modeling of complex systems. So we have done some work that looks at how we can use these dimensionality reduction techniques for optimal sensing and modeling. And so in this framework, we have a dynamic process that we're trying to track. So this process is changing in time, and we want to model it with a team of distributed robots. So the number of robots that we have is equal to K, which in this case is 5. It's the 5 yellow submarines that are in this environment, and the space is discretized, shown by the pluses. So everywhere that there's a plus, you can collect a sensor measurement, and then it's broken up into M candidate sensing regions, denoted by the white lines. So if you are a robot and you're within the confines of these white lines, then you're collecting sensor measurements over that whole region. And so we have these M candidate sensing regions and K robots, but in the M minus K regions where there aren't these yellow submarines, there are no sensor measurements being collected. And so using historical data or some forecast model, we come up with an initial set of principal components that describe the discretized workspace, and that comes from the PCA algorithm. And then we leverage the property of the orthogonal bases computed using PCA to actually determine where in the workspace would be best for the robots to go to collect sensor measurements so that they can provide an accurate reconstruction of this field in real time. And we want this to be distributed in terms of the models that the robots are building, and also in terms of the estimates of the time varying process. So in order to demonstrate the proposed framework, we have to dive in a little bit into this concept of gappy POD. And so in the original framework, in normal PCA, we have data collected over the full field, and we can reconstruct the model using the set of orthogonal bases in phi and C, which is a set of time-dependent coefficients. However, in the scenario that we're describing with the 5 submarines, we only have sparse sensor measurements. So we only have sensor measurements where those robots are located. And so gappy POD, in this paper, it shows us that the optimal reconstruction with only these sparse sensor measurements can be found using this formula. And then you just take these this optimal reconstruction in terms of the time-dependent coefficients and apply it to your original basis. So using this, we want to figure out where exactly we can place the robots to optimize this reconstruction. And so there is a theorem that says in order to optimize the sensing regions chosen, we have to minimize the maximum eigenvalue of the projection matrix A. And this is known as E-optimality in the design literature, if that is something that you have heard of before. And there's a physical interpretation of it, which says you have some subspace phi that's associated with the principal components that you calculated, and you have another subspace phi sub r that is a subspace associated with the principal components at only the sensing locations that have been selected. And so as these subspaces get closer and closer together, the projection error is actually reduced. And so we want to select sensors and sensing regions that will allow for this error to shrink between these two subspaces. So using some tricks from linear algebra, we know that we can actually just instead use a rough approximation that results in maximizing the minimum diagonal element of A. And this results in an approximation of choosing the sensing regions that are close to optimal in this case. So here we show the differences between the centralized and decentralized methods, where in the decentralized methods, robots can keep local estimates of the reduced order model and just take sensing measurements over their respective regions. So in the centralized framework, which is on the left, we have a global model, and that's combined with sensor measurements to update the field and update the model. And this reduced order model is computed through standard PCA. And then you put that model into an optimal placement framework that determines where sensor measurements should be taken. And then this PCA model and sparse sensor measurements are used in the GAPI POD framework to then estimate the full field. In the right, all of this is distributed. So this allows robots to keep models for regions, all of the regions of the dynamic process, collect new sensing information and adapt the models, but all in a distributed way. And so we're going to get into the specifics of this and how this is done. And so the first figure shows the environment. The leftmost figure shows the environment. And in that environment, the blue denotes regions with active sensor measurements. So everywhere where there's blue, you can imagine that there's a robot that's collecting measurements over that region. And the white denotes other regions that have models associated with them. So models that we got from either the historical data or forecast model, but they don't have any current sensor measurements. And so the dashed lines that we have here show how these different regions are assigned to different robots. And so the model of this environment can be represented and is represented through PCA as a matrix of eigenvectors. And the thing to note here is each row of the matrix actually corresponds to a point. So each row corresponds to one of those plus signs that we saw in the first slide regarding this work. And so you can give each row to the robots as the model of the environment. And they can keep on board the rows corresponding to their assigned region, so where they're actually taking sensor measurements. And at the bottom here, we see that robots can use their sensors and their neighbors' estimates and sensor measurements to actually estimate the field and update the reduced order model. And so the robots sense at their locations, they're assigned to keep track of local models of the regions for where there aren't sensor measurements, and then they use their own local model, their collected sensor measurements, and sensor measurements from their neighbors to estimate the value of the field. And then all of that is used to update the local model. In the experiments that we're going to show later, the communication is assumed to be all to all, but different communication schemes can affect the quality of the model. And so here we have some results. I'm sorry that you can hear police sirens. This happens every time I'm in a meeting. So here we present results on the reconstruction from the robots to the distributed method. And the thing to note here is that the error is exponential in the mixing time, tau. And the mixing time is a quantity that's associated with the graph of the communication network of the robots. So that's really interesting because it tells us that we can control the error of our reconstruction by trying to control the mixing time on the associated communication graph. So if we change the topology of the communication, that has an effect on the reconstruction error. So here we have a little video demonstrating this technique that we described, this framework that we described. And so we have a dye experiment that was completed in this green tank here. And the data from that dye experiment was projected onto our water tank, and the robots that we have in our water tank were able to collect measurements of the concentration of this dye and update the model accordingly that you see in the bottom in the black and white there. So you can see that we have this nice reconstruction. And the next work we did was how to introduce heterogeneity and how to deal with multi-scale data. So in this work, we're trying to address how we can accomplish modeling in an unknown complex spatiotemporal environment using a team of heterogeneous robots that are collecting multi-scale data. And so we have aerial vehicles that collect data with low spatial resolution. So you can see in this example here, they're collecting overhead images of water currents, whereas marine vehicles collect data with high spatial resolution, but at slower frequencies. So they're collecting flow field data, but it's coming in at a much slower frequency. And so what we want to do is be able to combine all of this data into one cohesive model while still maintaining the independence of the data sources. So the first thing we do is resolve this data to the same spatial and temporal frequency, and then we use DMD on this resolved data to elucidate the spatial and temporal behaviors of the system. And then we use those spatial and temporal behaviors of the system to guide the behavior of the aerial and marine robots. So DMD state reconstruction can be formulated as a function of the spatial modes, which are shown as V here, and the temporal modes, which are shown as lambda. And we can also use this for state prediction, so we can use this for estimation, but we didn't show that equation here. And so these temporal modes are used to determine the optimal sensing locations for the aerial vehicles, whereas the spatial modes are used to determine the optimal sensing locations for the marine vehicles, very similar to how we use the gap EPOD in the prior framework. And so in the previous framework, where we used gap EPOD, we wanted to minimize the maximum variance. But in this framework, we want to minimize the error in reconstruction by minimizing the volume of the error ellipsoid. And so this is a little different from the E-optimality design criteria that we had before, where now the objective is actually to minimize the determinant of this projection matrix. And so, oops, I forgot to play this video. And so we developed some matrix algebra techniques that allow us to do really fast greedy optimization techniques that actually allow us to figure out what the optimal sensing locations are using QR factorization. So the next thing that we looked at in this framework is how do we adapt the model? So we're gathering all of this information online, and what do we do with the acquisition of new sensing data. And so we want to compute the spatial and temporal modes for this new relationship, A prime times X prime equals Y prime, where all of these primes encapsulate the acquisition of new data. So we developed two techniques, the first of which is a very general adaptation scheme that allows us to do this online DMD decomposition without solving, without directly computing A. So instead we use some intermediate matrices to compute the dominant spatial and temporal modes. And a downside to this technique is we actually do have to hold on to all of the prior data that we collected. The second technique that we developed is a much faster method, but works well for a much smaller number of points. So we're looking at resolutions of, say, 200 spatial points. And this, in contrast to the previous method, does involve directly computing this A matrix, but we do not have to store the X matrix. We can store a compact representation of it. And so we have some results from an experiment. We had collaborators at the Navy Research Lab conduct or give us simulations of a barium plasma cloud. So they simulated how an artificial barium plasma cloud would move through the environment, and we use this data to test our algorithms. You can see in the first row the DMD reconstruction with homogeneous versus heterogeneous data looks fairly similar, but as time progresses and there's the introduction of these more complex features in these dynamic processes, the heterogeneity is better able to capture some of these features. And so these dimensionality techniques are quite fast, and they give us spatial and temporal characteristics of the system, but they're still inherently linear methods. And so we did leverage the fact that DMD has connection to the Koopman operator, but we can create stronger connections in terms of estimating these transfer operators and having more mathematically and physically sound ways of representing these systems. And so transfer operators give us a lot of information about the system. They capture the characteristics. They capture a lot of key characteristics about nonlinear dynamical systems. And we're going to talk about how we can approximate these transfer operators in data. But in order to do so, we first need to talk a little bit about kernel methods. So there's a lot of information on this slide. The main takeaways are that kernels and kernel methods represent similarities between points. And these points can be raw data. A second takeaway is that they can be used to create feature maps. So feature maps are a way of lifting the data that you have to higher dimensional space in the hope that you will be able to gain more information about that data than just looking at it in a linear space. And the third thing to note is that we have algorithms that can be expressed in terms of inner products can really easily be kernelized. So given the fact that we have this reproducing property, we can essentially take algorithms that use inner products and replace that inner product with a kernelized version. And so methods like PCA and also canonical correlation analysis, which we'll describe in a little bit, that are linear can have nonlinear extensions to this kernelization. So we're now going to present some results that this group did on how to extend transfer operator theory to reproducing kernel Hilbert spaces. So we're going to start with some preliminaries. We have state space, kernels, and feature maps that are defined on this data. And we also have these covariance and cross-covariance operators that are defined in terms of feature maps and can be approximated in terms of feature maps. So for the Perron-Frobenius and Koopman operator, we can actually express them in terms of covariance and cross-covariance operators. And since we can express them in terms of covariance and cross-covariance operators, we can approximate them with these approximations of the covariance and cross-covariance operator. So this is really great for us because now we have a data-driven approach for estimating the time evolution of probability densities and observables of dynamical systems. And this makes it really applicable to a myriad of robotic tasks. So the first work we presented, the first couple works that we presented really focused on these dimensionality reduction techniques. This work is shifting more towards using these kernel transfer operator approaches. So I'm running a little short on time, so I might skip a couple things, but in this ongoing work, we have kernel transfer operators that we're trying to apply to multi-robot modeling and prediction. And so we can use the spectral properties and linear prediction that comes from these kernel transfer operator approaches in a myriad of multi-robot applications. So we're going to dive into how we can use spectral properties of these kernel transfer operators. So we want to show how kernel transfer operators can be used to determine coherent sets of a dynamical system. And so what is a coherent set? A coherent set can be thought of as regions of the phase space that disperse really slowly. And so they can be used for determining optimal trajectories within an environment. The definition of a coherent set is that it's one that essentially remains unchanged under the forwards and then backwards dynamics of a random perturbation of the map theta epsilon, where the map theta describes the dynamics of the system. So I'm going to show a video that will elucidate some of these properties. So this is a Bickley jet. A Bickley jet is a benchmark problem in studying coherent sets, and it's an approximation of an idealized stratospheric flow. And so in this Bickley jet, we have two sets. One is black and one is yellow. And as time progresses, the black set you can see remains mostly intact, but the yellow one starts stretching and becomes fainter in these images. And so the black set is an example of a coherent set. So one that stays largely intact under the evolution of the system. And so these sets can be used in planning of optimal trajectories for fluids, ocean, and space. And they can be used, or they can be detected from onboard sensing data. And so coherent structures actually have a very nice connection to a tool in statistics called canonical correlation analysis. So in canonical correlation analysis, you say that you have two random variables, x and y, and you want to find two sets of bases such that when you project both x and y onto both of these set of bases, their correlation is maximized. And kernel CCA is just a generalization, a nonlinear kernelized generalization of CCA. And so these new bases can be found by computing the dominant eigenvalues and corresponding eigenvectors of these equations with the covariance and cross covariance operator. So you can solve for this, and you don't have to try and read all of the equations, but the important thing to note here is that this solution to the kernel canonical correlation analysis actually contains the kernel Koopman and Perron-Frobenius operator. And so the composition of these operators actually corresponds to a push forward and subsequent pull back of the density F, which is closely related and sounds very similar to this notion of coherence that we described. So in the original KCCA formulation that we use to find coherent sets, we have this eigenvalue problem. However, we can solve a surrogate problem that just relies on Gram matrices. And so in the surrogate problem that just relies on Gram matrices, we can collect data from aerial vehicles that represent the trajectories of individual particles within this flow field to actually understand where the coherent sets in this environment actually are located. And so why is this important? Why do we care about coherent sets? In order to motivate that, we're going to talk briefly about Lagrangian coherent sets. So they've been used in robotic settings. They are essentially separatrices that delineate where dynamically distinct regions in dynamical systems are. And so if LCS delineates dynamically distinct regions, then coherent sets are those dynamically distinct regions. And so another way of thinking about this is LCS is a geometric framework for studying coherence, while this transfer operator approach is a probabilistic approach for studying coherence. But they're essentially giving us the same information. LCS is an extension of stable and unstable manifolds to time-dependent systems. And given this knowledge, we've used LCS for planning energy-efficient trajectories in the ocean and maintaining desired sensor formations in the ocean. And so coherent sets can be used similarly. I'm just going to go through this last section really quickly. So we can also use these kernel transfer operators as linear predictors. So modeling and future state estimation is a really fundamental problem in robotics, and we can represent the environment directly using these kernel transfer operator approaches. We're going to focus on the Koopman operator because there's this connection to observables, which are essentially sensor measurements. And so why is this important? We can use tools and dynamical systems that describe what the characteristics of this Koopman operator is. We have kernels that allow us to represent the correlation between data in a rich way. And something that's really interesting is we can incorporate uncertainty in a really principled way. So in RKHS, you can embed a probability distribution, which gives you a way of saying you have sensor measurements that are noisy, and you can directly embed them into this RKHS. So a central problem to representing kernel Koopman operator is the ability to estimate these feature maps, phi and psi. And so the earlier work that we presented focused on computation based on Gram matrices of data. So we didn't actually have to explicitly evaluate the features. We can instead rely on this kernel evaluation, which is referred to as the kernel trick. However, in explicitly modeling the Koopman operator, we can't rely on this kernel trick. We have to explicitly model the feature map. And so these feature maps can sometimes be infinite dimensional, and they are tricky to model. There is a body of literature surrounding kernel learning techniques. So if we have data, how can we learn the form of these feature maps that expressively represent the data? But a lot of these works focus on univariate data and hold really strong assumptions about what the environment looks like. And given the fact that the environments that we are working in have a lot of unknowns and we don't have strong priors for what these environments are, these aren't viable assumptions to make. So in our setting, we're looking at frameworks to estimate both multivariate and more complex kernels. And so modeling complex nonlinear dynamical systems is really challenging. And despite this challenge, these systems characterize a lot of natural processes like fluid flows, oceans, and space. And if we want robots, and specifically multi-robot teams, to be able to operate in these environments, then it's necessary for them to incorporate the sensing information that they have into a map of the environment and use that map for planning. And so our work really focuses on this intersection of dynamical systems theory representations that are derived from machine learning techniques that can be used for optimal planning and explicit modeling and state estimation. And so this work that unifies machine learning and dynamical systems and transfer operator theory really advances the use of multi-robot teams in challenging environments like the ones we described. So I will end here and take some questions.
Great. Thanks so much, Tahiya. So we have a written Q&A interface in the Zoom webinar. If you have any questions, feel free to submit them. I'm joined by Tom Jang here, and we'll be asking the questions verbally to Tahiya. If you have any that you want to ask right now, Tom, you can go ahead and start.
Sure. Hey, thank you, Tahiya. That was a great talk. Yeah, I really enjoyed it. So I have a couple of questions here. So the first one is, you know, like maybe we have a lot of, you know, interested listeners who are doing machine learning. How would you compare your modeling approach to some other machine learning approaches, such as using RNNs to model dynamical processes?
That's a good question. That's not really something that we've looked a ton into. I think this work falls more in line with like Gaussian processes or occupancy mapping or using Hilbert maps for modeling and estimation. We have tried to do some benchmarks with neural nets, but it's been really challenging just given the high dimensionality of the data. I think moving forward, it's probably something that we can't avoid.
Okay, thanks. And my next question is on your experiments. So your experiments of using like multiple boats in the tank to monitor a process, it was like this like brilliant hybrid, you know, experiment and simulation. So I'm wondering, like, if the robots are actually putting the flow, so basically they are situated in the dynamical process itself, right? Like, how would that affect like your method?
So you're saying, what if there was an active flow in the tank?
Yes. So basically, like the robots are actually in the flow itself and it's trying to monitor that flow.
Yeah, that would be really tricky because of the assumptions that we make regarding sensing regions.
Right.
So in this case, we're saying we have this fixed discretization of the field and we're not considering any perturbations.
Okay.
And so this fixed method, this fixed discretization and this fixed categorization of the sensing regions would be really, really difficult in this moving flow.
Okay. Yeah, and also like any thought on actually like leveraging that flow to actually, you know, control the boats better to...
Yeah, so this is related to the work on coherent structures. And so the notion that's most similarly related to coherent structures are these Lagrangian coherent, or to coherent sets, is this notion of Lagrangian coherent structures. And LCS are actually used as a way of leveraging the flow. Danushka and Ani have done some work on this in the Scalar lab of how to actually leverage the flow for energy efficient trajectories. And so coherent structures can actually be used in a very similar way because they kind of serve as this dual to these LCS.
Ah, that makes sense. Okay. Yeah, and also I have a question about you already mentioned the priors and also like how much like knowledge do you have about the process, right? So when you're trying to do all these like reduced order modeling, say you are doing like PCA to find the top like few modes of a process. So like so in your experiments, like do you have some exploration period to gather some data first in order to like to reduce the order, or do you assume that you already have some data to do that?
Sure. So in the first work that was presented, our RAL paper in 2019, we assume that we have some historical model or some potentially noisy representation of the system, and that's used to begin with to create an initial model of the system. In the second work that focuses on heterogeneity, there is this notion of like an exploration period, of a period where you're just collecting data before you actually build a map and use it to determine the optimal sensing locations.
Cool. Yeah, and also I have a question about the performance measure of like adaptive sampling. So in different communities, they have like very different measures. So for example, for the CFD folks, they look like they will look at the long time average,
Mhm.
and in some other communities they might want like a a short time trajectory like prediction. They want that to be super accurate, and especially in some chaotic systems where you can't predict the long time trajectory. So in your case, if you're using PCA, you're trying to capture the most energy as possible, right?
Mm-hmm.
So like how would that affect the application of your method? So like is there a specific application that this is most like suitable for, or yeah?
Yeah, so PCA is good at capturing the most variance within the data set.
Yeah.
So it is well suited to capture processes that inherently have that variance uh, in the data set. Does that answer your question?
Yeah, so yes, I think that does answer the question. Yeah, yeah, that's good. Yeah, and I have like one final question about the feature map.
This is like rapid fire questioning.
Yeah. So like, yeah, because I think you answered all the questions like pretty nicely. It's exactly what I want to know. So like, I don't have any follow-up questions for those. Yeah. So my last question is about the feature maps that you were talking about for the kernel transfer operators.
Yes.
Okay. So so like what are they? Are they like some polynomial functions, or are they something that you have to decide like based on the system or the data, or do you have like, any intuition on how to choose those feature maps?
So that is exactly the question that we would like to answer, is how do you choose those feature maps? So for the coherent structure work, we are just using standard kernels, a Gaussian kernel, which gives us great results. The question that we would really like to know is, what do you do when you don't know what the feature map is? And that's where these kernel learning techniques are really important. But there's a rich body of literature that deals with these feature map approximations, but they are not good for realistic scenarios. And so that's really like a great question that we're actively trying to answer is how can we determine what these feature maps should actually be?
Right. And also I guess like we have a lot of empirical like knowledge about these systems, like the fluid or say some like some airflow. So we probably have some knowledge about them, but like if we are actually dealing with some model-free modeling, right? Like you have no knowledge about it, so we can't really escape the data, right? Yeah, I guess that's a fundamental challenge that we have to deal with. Yeah. Okay. Yeah, that's all my questions. thanks for your answers.
Of course.
Well, Tom has really done a number with the question, so I'll only ask one, and then we'll let you get out of here. So I'm very interested in this bound that you had on one of the slides earlier with the gap BPOD, and I believe you said that the thing that is dominating that bound that is most important is this mixing time. And I'm wondering, in practice and any experiments that you've done, do you think this bound is like practically very tight? Is it off maybe by a small factor, or is it like orders of magnitude smaller than you see in many of the systems that you work with?
This bound is, it really depends. So empirically, the bound tends to work better on smaller systems. So systems that are perhaps less detailed, if that makes sense. I'm not sure exactly why. Yeah.
Are there any other terms in here that you think about as being important, or maybe things that don't show up in this bound but seem to be driving accuracy in practical experiments?
I think actually, to be quite honest, the greatest indicator of accuracy is the historical model that you have, because this method is dependent upon having this forecast model, which is actually one of the motivations for exploring the second technique that we had, where we didn't start with any data.
Okay, great. That's my most important question. So thank you so much for coming to speak to us today, and thanks everyone for attending and joining us for this talk. And we'll be back next week with another speaker, Matthew Piccoli from industry. All right, thanks so much, everyone.
Thank you.
Thank you.